Well, welcome back to second semester. And we're going to start off by skipping chapter 12, which pertains to rate law. That's all stuff that you did at the end of the year in honors chemistry, so hopefully you saved all your notes. I'll have some review material for rate law at the end of second semester as we get closer to the AP exam. So we're going to start with chapter 13, which deals with something called equilibrium. And an example of a reaction that we might consider would look like this. This is a compound called dinitrogen tetroxide that decomposes to two molecules of nitrogen dioxide. And you might recall that we did this at the very beginning of the year in honors chemistry by throwing a penny into nitric acid. And we got this very dark brown noxious cloud. That's this stuff. So it's dark brown. And this N2O4 stuff is perfectly colorless. So when we let this reaction run, what we'll see is that the color of NO2 slowly forms out of nothing. And you get something that kind of looks like this. Of course, this is a sealed container. This vessel is sealed. And here is our colorless N2O4, and this is our dark brown NO2. And a lot of people would look at this reaction and say, well, the reaction goes until all the N2O4 is used up. Now, that's not quite how it works. So let's take a look at a little chart of what's going on here. And what we're looking at here is a graph. We've got concentration on the y-axis. We've got time on the x-axis. And this NO2 is represented by this kind of orange line here, starting here. And our N2O4 is this blue line that is starting here. And check out what's going on. When the reaction begins at time 0, the concentration of NO2 is 0. There isn't any in the reaction vessel. The concentration of gases in the reaction vessel is entirely N2O4. But as the reaction runs over time, notice that the concentration of NO2 slowly rises and begins to fall off until eventually flattens out. And the concentration of N2O4 decreases, and then eventually it also levels off. And what's going on here is represented by these two arrows that are pointing in both directions. And that means that as we get to a certain point, we reach what's called chemical equilibrium. It isn't that the reaction stops running. It's that it runs in both directions simultaneously in such a way to keep the ratio of concentrations of reactants and products completely constant. So if we were looking at this graph and we were saying, okay, well, that's 0 and that's 1 and that's 2, that at equilibrium, the concentration of NO2, which we'll put in brackets, is roughly twice that of the concentration of N2O4. And this is basically what equilibrium is. And this ratio, let's say that in this situation, that the ratio of these two chemicals was 2 to 1. We're going to call that K. And that's going to be our equilibrium position. And at equilibrium, the ratio of products to reactants, in this particular case, would be 2. That's a constant. It means that for this reaction, when it reaches equilibrium, the ratio of products to reactants is always going to be 2. All right, let's take a look at how we're going to do this because the calculations are pretty simple. So let's take an equation. A plus B reacts to produce C and D. And we're going to start writing this arrow a little differently. We'll indicate that this reaction is at equilibrium by pointing this arrow in opposite directions. And let's pretend that we have the following stoichiometric ratios. They're just letters that represent numbers. I'm not using L because it looks like a 1. So, at equilibrium, we're going to represent equilibrium with this letter K. A lot of people call that K sub EQ. We're just going to say K. This is the equilibrium position. It is the ratio of products to reactants when we reach equilibrium. So we're always going to put reactants on the bottom and products on the top. And so for a reaction that looks like this one, what we'll say is that K is equal to the ratio of products, concentration of C times the concentration of D, raised to their respective coefficients, M and N, over the reactants, A and B, raised to their respective coefficients, J and K. And this gives us a value that tells us what the equilibrium position is. It's a number that tells us that the ratio at equilibrium is this versus that. Let's take an example and I'll show you how this works. All right, here's an example. It says calculate the equilibrium constant for the following reaction. Ignore this little C right here. We're going to worry about that tomorrow. Right now, this is equilibrium for concentration. Tomorrow or later on in the week, we'll be looking at gases, and then that'll be an equilibrium of partial pressure. Right now, we're just talking about molarity. So we've got 3 gases involved here, but we're going to calculate their equilibrium position in terms of concentration. Okay? So it says calculate the equilibrium constant, in other words, the equilibrium position when this reaction runs until it reaches this position of equilibrium. And it gives us the concentrations of each. So the first thing that we're going to do is we're going to write the equilibrium expression. We're not going to calculate anything just yet. So the first thing we're going to do is, oops, I should spell it correctly. Happy 2021. We're going to say, can I write the equilibrium expression for this reaction? So that means we want to find out what K is going to be equal to. And it's always products over reactants. Well, we have only one product. That is hydrogen iodide. And it has a coefficient of 2, so we'll raise that to the 2nd power. On the bottom, we have hydrogen gas and iodine gas, and they have a coefficient of 1. We know that because there's nothing there, so we're not going to use a coefficient. We're not going to raise these to any power. What we are going to do is write the equilibrium expression. And the cool part about equilibrium expressions is they're just a ratio, so we're not worried about units. So don't panic if the units get all weird. We're not worried about that. In a lot of cases, they cancel out, but it's just not something that we spend time on. So the second part for this would be calculate K. In other words, what is the ratio of products to reactants when this reaction reaches equilibrium? And what this data is saying is that these are the concentrations right here. When this gets to equilibrium, this is where everything stops. This is like that graph that we were looking at for dinitrogen tetroxide to nitrogen dioxide. So this is a pretty straightforward setup. This is exactly what the concentrations are when the reaction reaches equilibrium. So we're going to plug these data right into this equation. We're going to say, okay, let's calculate K. We know that it is HI squared over H2 raised to the 1st power and I2 raised to the 1st power. And here's our data. At equilibrium, Concentration of HI, 0.389 molar. So that's going to go on the top, 0.389, and we're not worried about the units, so we'll just ignore those. On the bottom, we have the concentration of H2, according to this, 0.0505 molar. So 0.0505 molar. We're not worried about the units. And finally, the concentration of iodine. Right here, it tells us 0.0498 molar, and that's going to go right here, 0.0498. And we're not worried about the units. I just told myself that. Okay, let's bust out our fancy calculator. And it's been a while since I've used this thing. Let's see if it works. Wonderful. I'm going to put this over here so we can see what's going on. You can do this all in one shot, or you can do it in a couple of steps. I'm going to do it all in one shot. So we're going to say 0.389 squared. We're going to divide this by the quantity of 0.0505 times 0.0498, and close these parentheses so the calculator knows that that's done, and this should tell us our equilibrium position. It says that at equilibrium, the ratio of products, that's HI, to reactants, that's hydrogen gas and iodine gas, is 60.2. It's just a ratio, so we're not worried about units. What this says is that at equilibrium, the concentration of products is roughly 60 times greater than that of the reactants. So when the reaction runs, it almost gets to completion, but not quite. All right, that's the whole thing, and for now, that's about as complicated as it's going to get. So I'd like you to try a couple of these, and I'll see you all on the next one.